Hi everyone, welcome to this presentation entitled Transformer Operation with a Half-Wave Rectifier. This is the outline of this presentation. We will see first an introduction, then we will analyze the operation of the transformer with a half-wave rectifier. We will show the operating waveforms of the transformer when it is operated with this type of rectifier. We will show some LTspice simulations to verify the analysis, and finally we will also show some experimental waveforms. Let's start first by stating the problem. Here we have our transformer. We have a core with a given length, LE, a given cross-sectional area, AE. It can also have an air gap, G, and then we have the primary winding and the secondary winding. We are applying a sinusoidal voltage across the primary winding, and we are placing a diode at the secondary with a resistive load. So here we have the theoretical waveforms. We have the voltage at the primary, the voltage at the secondary. We are assuming that we have a step-down transformer. And here are the theoretical waveforms for the currents. We have the current through the primary and the current through the secondary. However, we can see that here we have a DC current level in the currents through the primary and through the secondary. So there is a typical question here, which is the following. Is there any DC component in the magnetic flux density? And if so, is there any risk of the transformer operating in the saturation region? So it can be dangerous for the transformer to reach a saturation region and increase the current circulating through the primary, which can increase losses and decrease the efficiency of the transformer. So we are going to try to answer these questions today by analyzing the operation of the transformer under these circumstances. Let's analyze first the ideal situation. We are going to consider an ideal transformer in the sense that there is no leakage inductance, there is no series resistance in the primary or in the secondary. So we have only the magnetizing inductance, and then we have this equivalent circuit for our transformer. So we are applying a sinusoidal voltage at the primary, and we can do the following reasoning. First, we are applying a voltage V1 at the primary. So we have the Faraday's law. All the flux is going into the secondary winding. So using again the Faraday's law, we have the voltage at the secondary, which has to be like shown here by this equation. Using these two equations, we have the relationship of the voltages, which is the ratio of the windings turns. Also, we are considering everything ideal, so the input power has to be equal to the output power, and therefore the ratio of the currents in the primary and in the secondary has to follow this expression here. Is again the turns ratio of the windings number of turns. So with these equations, if we have a voltage V1 as shown here, then we are going to have a voltage V2 as shown here. Because we have a single rectifier here at the output current I2 is going to be as shown here in blue. And therefore, using this expression that we have just seen, we have the current through the primary also, which is proportional to the current through the secondary. We can also calculate the flux in the core, which is this waveform here, that can be obtained by integrating the voltage V1, for example. So we integrate the sinusoidal voltage here, and then we get the flux as given by this expression here. So considering the ideal transformer without series resistances at the primary or at the secondary, a perfect ideal transformer, we can see that the operation should be like this. And it seems like the transformer is even transforming DC currents, because we have a DC current at the secondary and we have a DC current at the primary, and they are going to be in the same ratio as the turns ratio. However, there is no ideal transformer, and we are going to have always a series resistance here at the primary of the transformer, which is the series resistance of the winding. And this series resistance is going to generate a DC component of the voltage here that at the end is going to be applied to the primary of the transformer across the magnetizing inductance, and therefore there is going to be a DC flux generated in the transformer. Let's see how to analyze this. We can use the superposition principle here because we have a linear system. Therefore, we can consider only the DC circuit at the primary. So we make 0 the input voltage source, and we consider here the current circulating through the primary of the ideal transformer, this current here. We consider here the DC component of this current, which can be calculated as shown here. So we have this simple circuit. From this circuit we can obtain also this model here very easily, and therefore we can see that there is going to be a transient in which we are going to have a DC current circulating through the magnetizing inductance. It's going to be a transient, an exponential transient, and the DC component of the magnetizing inductance is going to evolve as given by this expression here. Actually, this is a simplification, and the calculation of this transient is much more complicated because this magnetizing inductance is going to change as we are entering into the saturation region of the BH curve of the material. When we enter into the saturation region, the permeability of the material decreases, as we know. This increases the value of the reluctance, and therefore the value of the magnetizing inductance decreases. So this transient is going to be shorter than in the case that we consider constant value for the magnetizing inductance. So this is the situation of the DC component in steady state. The magnetizing inductance behaves as a short circuit, and the DC current is circulating through the magnetizing inductance in this way, as shown here. We have a short circuit here which corresponds to the voltage source, to the AC voltage source. So the voltage in a steady state, the DC component of the voltage across RS is 0, and therefore all the current is circulating as shown here through the magnetizing inductance, and this DC current is going to generate a DC magnetic flux in the transformer. We are showing here the BH curve of the material, so we are going to have a DC component of the magnetic flux density and a DC component of the magnetic field intensity. We can calculate this value of the DC component of the magnetic flux density as shown here in these equations. The DC component of the flux is the DC component of the magnetomotive force divided by the reluctance. The magnetic flux density is the flux divided by the area. And the reluctance can be obtained with this expression, in which we have the permeability of the material, which is a function of the DC component of the magnetic flux density, because when we enter here in the saturation region of the BH curve, the permeability is going to change, is going to decrease. So it's a function of the DC magnetic flux density. And then we have here this value which corresponds to the area gap over the permeability of the free space times the cross-sectional area. From these equations, we can obtain, if we wish, the magnetic flux density, the DC component of the magnetic flux density. We are not going to enter into detail here in this presentation. You can find more information about how to solve this type of equations in this video, Power Electronics number 13, entitled DC inductors and their non-linear operation. Now we can continue using the superposition principle to calculate the AC component of the different variables in the transformer. So we have this equivalent circuit in which all the variables correspond to the AC component. So we are using the hat symbol to designate the AC component of all the variables. We are considering here the input voltage, which is an AC voltage, and in this circuit we can do a simplification because this series resistance is usually very small, so the AC component here across this series resistance is going to be negligible in comparison with the input voltage, so we can obtain this other simplified circuit. In this circuit we are applying the input voltage across the magnetizing inductance directly at the input of the transformer, so we can use the Faraday's law to calculate the flux that we are going to have in the transformer, the AC component of the flux. So if this is the input voltage, a sinusoidal waveform, we know that the AC component is going to be like this, a cosinusoidal waveform with a minus sign, and therefore we can obtain also the AC component of the magnetic flux density by dividing by the cross-sectional area. So we have this expression here. So at the end we have something like this. We have a cosinusoidal waveform for the magnetic flux density. If we use the BH curve of the material, the characteristic of the material, then by knowing the DC component and the AC component that we can obtain from this expression, then we can obtain from the characteristic the AC component of the magnetic field intensity. So we can see here that because we are operating in the saturation region of the BH curve, the magnetic field intensity is going to be highly distorted. We have a small component here in the positive side and a very big amplitude here for the negative side of the magnetic field intensity. And this magnetic field intensity is directly related to the magnetizing current circulating here through the magnetizing inductance. In fact, we can calculate the relationship between magnetic field intensity and magnetizing current using this expression here, which comes from the well-known Ampere's law. So the magnetic field intensity in the core times the length of the core. We are neglecting here the effect of the air gap in the length, so we are approximating the length to the length of the complete core, plus the magnetic field intensity in the gap times the air gap length is equal to the number of terms times the magnetizing current. And from here we can obtain finally this expression. Usually in transformers the air gap is very small. We can neglect here this term now to simplify, so we can say that the magnetizing inductance is going to be proportional to the magnetic field intensity. So the shape of the magnetizing inductance is going to be something like this, also with a very high distortion. So now we can see the final waveforms that we are going to have in the transformer, which is the composition of the DC components and AC components of the different variables. So here we can see the input voltage V1, which is a sinusoidal waveform. We have here in blue the magnetic flux density, the minus 1 times a cosinusoidal waveform. Here in blue we have the current through the secondary transformed into the primary, so is the current that we have here is N2 over N1 times the current through the secondary, which is the rectified waveform. And then we have the magnetizing inductance, which is a waveform as shown here, which is obtained from this waveform is proportional, as we have seen, to the magnetic field intensity. So it's going to be something like this, is the current circulating here through the magnetizing inductance. So finally, the current that is going to circulate through the primary is the addition of these currents. So I1 is equal to the magnetizing current plus the current I2 prime, is the addition of these two currents here, and therefore we have an evolution of the current in time as shown here. So the ideal situation would be to have a rectified waveform here, perfect rectified waveform as shown here, because if the magnetizing inductance is very high, this current is going to be negligible in a normal situation without the rectifier, just applying the resistance to the secondary. We will have here a sinusoidal waveform for the magnetizing current with very small amplitude, but because of the DC component of the magnetic flux density, we enter here in the saturation region, and therefore the magnetizing current is distorted. So we have this waveform, and these peaks at the end are translated into the current in the primary. So we are going to have a much higher value of the RMS current through the primary, and this will cause higher losses in the transformer. So this is the reason why the use of a half-wave rectifier is not recommended at the output of a transformer. So now we are going to do a simulation in LTspice to verify the operation of the transformer with the half-wave rectifier at the output. Here we can see the transformer. This is the primary winding, this is the secondary winding. Here we have the reluctance of the core. We are using reluctance with N87 material, so these are the parameters of this reluctance. And here we have the air gap. It's a very small air gap of 50 micrometers. And then here we have the output. We have both possibilities. We can place the diode, or we can short circuit the diode to demonstrate the operation in linear mode. And then here with this circuit we are obtaining at this point the magnetizing current. We are doing this by subtracting from the current through the primary the current through the secondary reflected into the primary, I2P. So with this we have also here these statements to calculate the value of the magnetizing inductance. Of course, these calculations are only valid when we operate in linear mode. This is without the rectifier diode, just applying the resistance to the output, but we can also use these calculations when we are using the rectifier to demonstrate that the value of the magnetizing inductance is going to decrease when we use the rectifier at the output. You can see here these special elements to model the transformer. These come from our magnetics library. This library is available from my website. And in this video here, Power Electronics number 5, SPICE modeling of magnetic devices, you can get more information about these components. And here we have these other components, the current sensors, the subtractor, the gain. These are available from our Simulink compatible control library that is also on my website. And in this video, LTspice number 11, you can get more information about this library, and there are other 3 videos about this library also on this channel. So now we can run the simulation. Now we are going to do the waveforms when we are not using the rectifier, just by placing the resistance across the secondary. So let's run the simulation. And here we have the results. So we can see the primary waveform, the voltage at the primary in blue, the voltage at the secondary in red. We have here the currents. In pink, we have the current through the secondary. In blue, we have the current through the primary. We can see that they are perfect sinusoidal waveforms. Here we have the magnetizing current, which is very small compared with the current through the primary. Here the current through the primary is something like 12 amperes, while here the maximum value is lower than 180 milliamperes. And here we can see the waveform corresponding to the magnetic flux density. So the peak-to-peak value is something like 300 millitesla. So this is the normal operation of the transformer without a rectifier and diode at the output. Now we are going to do the simulation by placing the diode at the output. So we can cut this wire here and run the simulation again. And now we can see how the waveforms have changed. We have the primary in blue, the voltage across the primary. Now the voltage at the output is the rectified voltage. And here we can see the current at the output, which is also the rectified waveform. But now the current through the primary, we can see the waveform that we have seen before. Here is something similar to the rectifier waveform, but we have this peak corresponding to the operation of the transformer in saturation, because here we can see the magnetizing current and we see how we have this huge peak here, which almost is 27 amperes, which is due to the operation of the transformer close to saturation. Because here also we are showing the magnetic flux density, and we can see how we have a DC level in the magnetic flux density now due to the operation of the rectifier. We can check this. The average value is something like 416 millitesla. So we have a value which is well into the saturation region. We have material N87, which has the saturation region starts around 400 millitesla. And we are going beyond this point because here we are reaching almost 600 millitesla. And also we can do another test, which is the following. If we increase the value of the load resistance here, the average current is going to be lower. So the peak of the magnetizing current is going to decrease also. Here now we have a peak of 27 amperes. Now if we increase this to 10 ohms and run the simulation again, then we can see that now the peak is much lower, is something like 13 amperes. Also, the average value of the magnetic flux density has decreased. We can also do the test of checking the value of the magnetizing inductance. We are going to do this first using the linear operation of the transformer. Let's put here again 5 ohms and then run the simulation. So here if we press Ctrl L, we can see the results. So the magnetizing inductance is something like 3.1 millihenries, which is the normal value of the transformer operating in linear mode. But if we operate with the rectifier and run the simulation again and then press Ctrl L, we can see that the value of the magnetizing inductance is much lower, 43.6 microhenries, which is much lower. Of course, this is not a real calculation of the magnetizing inductance because we are operating in the nonlinear region of the BH curve, so it doesn't make much sense to talk about a value of the magnetizing inductance, but we can see that this value is much lower, and this is due to the effect of the decreasing of the magnetic permeability of the material when we enter into the saturation region of the BH curve. Finally, we can see here real-life measurements. We have used a small transformer here with an input voltage of 230 volts, an output voltage of 7.5 volts, 2.4 volt amperes. We have used a series resistance of 500 ohm to measure the current through the input, and then we have placed a rectifier and a load, and these are the waveforms that we have measured for different values of the load. For 22 ohms, here the scale of the current is 10 milliampere per division. Here is for the case of a load resistance of 11 ohms, so we can see that the peaks of the current increase in both sides. And here is for the case of short circuit at the output. So here we have higher value of the current and also higher value here at the peak. So we can see that the higher the current at the output, the higher the saturation of the transformer and the higher the peak current that we are going to have in the primary. Well, this is the end of this presentation. I hope that you find this video interesting. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.